Hello, future engineers. Welcome to my YouTube channel. If you're still new to my channel and you like what I'm doing, please don't forget to subscribe and share my videos to your friends and to your friends' friends. That's the only way you can help me promote my channel and to keep me going, refreshed, and inspired. And I'm very willing to share my knowledge, especially topics in civil engineering for your benefit. So this problem is a selection design problem. Actually, we already solved problems designed for bending and flexure where we computed the safe load or dimensions. That's part of the design proper. But this is an example where we have to select sections from tables of steel sections. The working stress in bending for the simply supported beam is 120 megapascals. Find the lightest W shape. So when we design, we should select the lightest W section so that it is the most economical but satisfying the requirements, strength requirements. So W shape that can be used and calculate the actual maximum bending stress in the beam selected. So the actual maximum bending stress incorporates the the weight of the beam because as a preliminary design, the weight of the beam is not yet known. So we should include that as we analyze the situation. So we have a load at the center where the maximum moment is PL over 4 and a uniform load which covers the entire simple span. So the maximum moment is also WL square over 8. So therefore, Mmax is PL over 4 plus WL square over 8. So Mmax is 40 times 10 over 4 plus 20 times 10 square over 8. So therefore, the maximum moment is equal to 350 kilonewton meter. Then stress is my over I in general or mc over I. The ratio of I over C is section modulus in mm cube. So it is also m over section modulus. So in this case, because we have to select W shape and we do not know the depth yet because we do not know the lightest W shape, that's why we compute the section modulus instead. So substituting 120 should be greater equal to 350 times 1000 square to convert kilonewton meter to Newton mm divided by section modulus so that the section modulus should be greater than equal to in mm cube. So 2.917 times 10 to the 6 mm cube. So next we have to find in the tables different W shapes such that the section modulus should be greater than this and it should be the lightest. Now, which of the sections will be the lightest? The second number. The first number is the depth, nominal depth, and the second number would be the weight in kilogram per meter if it is in SI. In this case, it should be in SI. So we have here the clippings from the table where I only select sections. There are more sections here. I only select sections where it satisfies this requirement. Section modulus should be greater than 2.917. So 3000. This one uh, does not satisfy because it is only 2.83 times 10 to the 6. this is 10 to the 3. So divided by 1000, so that would be times 10 to the 6. So for W360 by 262, we have W360 by 179. Take note, 179. 360 by 179. The actual section modulus is 3.11. 3.11 times 10 to the 6. So it satisfies, but it is heavy because it is 179. For the second, we have W310 by 313, which is heavier than the first. So far, 360 by 179 controls. Then for W460 variety, we have W460 by 144, which satisfies the requirement. So it is lighter than W360 by 179. So far, these controls. This will be our updated selection. But for W610 by 241, we have W610 by 125, which has actual section modulus of 3.21 times 10 to the 6. And this is the lightest among these varieties. So therefore, we select W610 by 125. So among these, there are other varieties of W sections, but they are heavier. So you proceed to the appendix of the textbook, and you can find the different varieties there. Then select the lightest W section. So this is the lightest W610 by 125. The actual section modulus is 3.21 times 10 to the 6, which is greater than this required section modulus. So therefore, the sigma max is moment actual divided by section modulus actual. The actual moment is 350 plus the additional moment due to the weight of the beam. The weight of the beam is 125 kilogram per meter times 0.00981 kilonewtons per kilogram. So weight of beam is 1.226 kilonewton per meter. Therefore, the actual moment is 350 plus W of beam, L square 10 square over 8. So moment actual is 365.32 kilonewton meter. Then substitute. Sigma max equals 365.32 times 1000 square Newton mm divided by section modulus actual 3.21 times 10 to the 6. So 365.32 over 3.21, that's the actual maximum bending stress, which is 113.8 megapascals, less than 120 megapascals. Therefore, it is safe. So that's it for this problem.